displayed here. Okay. So you can also execute this trace. Okay. So while executing trace, the normal trace and this trace will you can see some difference. Okay, start time duration. There some duration is missing. Okay, this is for the same program. Okay, array addition program. Okay. What about the grid X, grid Y, grid Z? So if you have used all these things, that will be displayed. Here we didn't use any grid X, grid Y, and block X, block Y, block Z. Okay, so nothing is seen here. And what about the bytes? Dynamic memory usage, how many bytes, throughput. So all the things have been displayed. And also you can GPU trace in you can import in CSV format too. Okay, that you can also available, and so you can also store it in SQLite. Okay, database. So all the reports you can store there, and processing time report don.sqlite. Okay, the number of calls, average, median. Okay, all the things available. So next we'll be having while installing NV site, everything will be installed. Okay. So here, uh, so I have checked, I have imported that NCU, that is N compute command. So this is the command line interpreter. So can you import this? So after that, you can check the version. It's available. So here you have to off the prefetch operation and use NVProf. Okay. So after that, how many number of devices has been used? You can give. See here the same NVProf results. You can get all those results. Okay. After that, I have executed one. Uh, okay, the same program only. The same program. So I have what I have done is first for visualizing the end site. Okay, so I have executed some commands. Okay, so I'll show it. And first you have to off the prefetch, and next you do NVProf. Okay, we'll get all those things. Okay, the same thing. Okay, so here the main thing is you have to off the prefetch. Okay, visualizing. Same you will get, and so here in this statement, what we'll get is we'll get some additional values. Okay, so what the time taken for pool IOCL. Okay, all those things we'll get, and so you can also get the reports. Okay, that is all reports. This is the same command. So after completing this one, what you have to do is I'll show the link available. Okay, this is a link. In this link, you can follow for anybody needs insight uh, profiling. You can follow this particular link. So it is available. So after that, what I have to do is I have to execute this statement. Okay. So now I couldn't execute because the runtime type creates some problem. Will come with attention. I think it is available. Whether it is running or not, I don't know. Previously, I didn't execute it. We have to do is we have to import something. Yeah, the Qt initialization is failed. Okay, there is one small error. So you use either this one or that one. Okay, see, you will get this particular window. Okay, you can launch, you can create new project, everything. So after that, you will get some visualization activity. Okay, those things you will get. Okay, that part I couldn't do. Up to this, I have done. Okay, so you'll get a small glance about that. So we'll move to today's class. Here I have given all the so links for references for visual profiler. Okay, you can follow that. So there is one person has uploaded one video related to that. But there, what you have to do is you have to download the report, and after that you have to open the report. The report is not opened in my laptop. Okay, that's why I couldn't able to show you. Okay, you follow these references for profiling. Okay, so in today's class, we'll see what is dynamic parallelism, how we can process multi-GPU, what is warp voting, everything we can see now. So dynamic parallelism is nothing but we are dynamically allocating memory. So while launching the kernel, okay. So if we are having some nested for loops, okay. So that time sometimes we may have needed of nested parallelism. Okay, this dynamic parallelism is very much useful in nested parallelism. So, okay. So here the algorithms for dynamic parallelism is in hierarchical data structures. A lot of recursion is needed, and each level of recursion you need parallelism. And algorithm is split into independent batches, and each batch involves some parallelisms. Okay. So here all the parallel loops need to be dynamically parallelized. See here there is one program. So how to execute dynamic parallel programs? See here STD. Sorry, here we are having two kernel program. One is child, another one is parent. Okay, and it is assigned with some thread ID, and the child is called here in the parent kernel. So with the argument of thread ID. So in the main program, we have called here with one block, three threads, and the device is synchronized. If you have executed using this particular NVCC, so what happened is you will get some error. Okay, because both are global functions, you are calling one kernel from another one kernel. Okay, so calling a global function child from a global parent is only allowed on compute 35 architecture or above. Okay, so what we have to do is so in the initial first day class, what I have done is I have given some architecture names there along with the NVCC. Okay, so if you give this one, it will be executing. Okay, so if you have two kernels, you have declared globally, one kernel is calling another one kernel. That means here this parent kernel, in that parent kernel, we are launching the child kernel. Okay, so we are calling. It is allowed in compute 35 architecture or above. Okay, if your system is having device which is compute 35 architecture above, then only we can able to perform these operations. Okay, so we'll be getting the output, and so here it is printing the process IDs. Okay, initially parent 0, 1, After that, we'll try this one. And today morning, in my laptop, I couldn't able to execute. Now only it get readied. Uh, so I will try this here. Oh no. What do you have to do? We'll try now. What happens? Okay, so kernel launch from device or global function requires separate compilation mode. Okay, so that is the error we are getting here. Underscore 35. RTC equal to true. So the warning is there. I don't know whether it is 35 or 39. Okay, so anyhow, we are getting the result. Okay, so we have to give in this way. Okay, so here what we are doing is, so there is child and parent. Okay, so we have used the thread IDX. Okay, key value is given as 2. Okay, we are getting only the what is called even numbers. Okay, so if it is equal to 0, there is one condition is given. If that condition satisfies, what it is called is, it is calling the 1 comma k. That is one block, two threads. Okay, so with the argument is thread IDX. Okay, so next it is called here, and after that the past value plus and thread IDX value is added together, and it is returned back, and it is called with called children with the starting what value. Okay, so that is done here. Then we are having kernel launch 1 comma 10. So 10 times it will be repeating. In between that 1 comma 2. Okay. While incrementing kernel, what it will do? For even values, it go there, and for the this is added together and it is printed again. Okay. That happens here. So it is dynamically executing. That means dynamically parallelizing. So here what happens is one kernel is associated with one grid, another kernel is associated with another grid. And both the kernels may execute asynchronously. Here we have written parent kernel and child kernel. That's why it's given like that. In general, we are having two kernel. Okay, so one kernel is associated with another one grid. You know the hierarchy. Okay, then only it will be VC. See here also we are calling the launching the kernel. Here also we are launching the kernel. We may have some doubt. So both the in main function also we are launching kernel, and the global function also we are launching. What happens is, so here each and every kernel is so associated with its own grids. Okay, and it is executing different block and different threads. Okay, not same block and same threads. Okay, so both the kernels may executed asynchronously, and so what happens is the main grid is not completed unless its children in the sense, so inside that particular kernel that have completed. Okay, and here both the kernels share global and constant memory. Okay, the memory is shared by both the kernels. Okay, it is not a problem, and but they have distinct local and shared memories, because each and every one kernel is having a separate grid means, so they are having their own local memory and the shared memory, and all global memory operations in the parent before child launch are visible to the child. So all the global memory operations are visible because the global memory is shared by both the kernels. And so, but the reverse process after synchronization only, the parent synchronize on the child completion. So once the child process is completed, then the parent will synchronize it. Then only it can able to visible to that. Okay, so these are all memory related issues, and you can also use multi GPUs in a single program. Okay, one CPU may attached with multiple GPUs. So multi GPU means multiple devices are there, and CPU may have different type of devices with different compute capabilities. Okay, so if any workstation may, so based on the requirement, if the requirements are satisfied in a particular workstation or server, you can use multiple devices. Okay, multiple GPUs with the different computing capabilities. Okay, so all the GPUs have been numbered from 0 to n minus 1. Okay, so you can also set the numbering. I see here there is CUDA set device 0 and one kernel is launched. So CUDA mem copy and CUDA set device 1. Another one is CUDA mem copy. So if you need some parallelization, okay, what happened here is first device 0 is completed. Everything after that device 1 goes to its execution. Okay, and if you want to need parallelization, what you have to do is instead of CUDA mem copy, so you have to use CUDA mem copy asynchronous. Okay, so here both the, if any two GPUs are available means both the GPUs will be asynchronously executing their own kernels launched in that particular program. Okay, so this is the difference. And if you are having multiple devices, in the sense you may use some of the APIs available in the CUDA framework. CUDA get device count. So it will return the number of devices in that particular machine or CPU. And CUDA device can access peer. Okay. So it means the current device cannot directly access memory from peer device. Okay. So one device cannot access the memory of another one GPU device. Okay, and you can check whether it can able to access or not. So it won't directly access. If you want to access, need to access, you have to do it in some other way. And see here, one more API is available. CUDA device enable pure access. Okay, what it will do is you can give the peer identification key here. Enable direct access to memory allocations on a peer device. Okay, so if you have used this API, it will provide the direct memory access. In the hardware level, the relation is symmetric. The programming interface provides the asymmetric. Okay. So normally, if you are having any number of devices, that will be executed in a symmetric way. Okay. So if you want to execute all the devices parallelly in programming way, you have to give. Otherwise, it will be in default case. So it will be executing in a symmetric way. Okay. So here we'll be having 8 pure connections per device. Okay. So for a single device, you can connect 8 pure device, and you can do it for 64-bit application. Okay. No, for not below that. So you can numbering the devices. Okay. In device count, you can get CUDA get device count. So it will return how many devices are available, and so device properties and CUDA get device properties. You can do that. So here you can get the compute capability of all the devices connected in that particular CPU. Okay, so next one is VART voting, and so if you are having
domain.
Just a minute. So you know what is a warp? Okay, so collection of 32 threads. That is called a warp. Okay, so here CUDA programming introduces some new concept like warp coding. Okay, so we'll be having three functions: all, any, ballot. Okay, so if that any conditions inside that argument that is satisfied, okay, so that time what it will do is you can perform some atomic operations. Okay, and here the predicate is non-zero, then only you can able to perform all. So here all warp threads satisfy the predicate. Okay, what are the condition you have given? That has to be uh, satisfied by the all 32 threads. Okay. Otherwise, you can use any. Okay. So in this any function, if any warp thread satisfy the predicate, so it will be executing. And so there are different versions are also available. Ballot predicate. So it will return which warp thread satisfy the predicate. So okay, which one is satisfying the predicate, that will be given. Okay, so normally it will be generalized with the help of all and any. And here there is one uh, histogram, CPU histogram is, that is CUDA histogram is available. Okay, and so using that, this voting is mainly useful for reduction. Okay, so already we have seen the reductions. Okay, and for the reductions, you can use it for reduction operation. So it is something like our atomic operations. Okay, and so what the ballot predicate will do is it will um, evaluate the predicate for all the active threads. If all the 32 threads are active means, so it will calculate it for evaluate the predicate for all the 32 threads and returns the integer value which says that which thread evaluates the non-zero for the predicate. Okay, and so that happens here. You can use it for reductions. Okay, so already we have seen the reductions in atomic operations. Okay, so try to execute this program. given the name W. I shouldn't give it this one. Okay, so it also shows some warning. Okay, here we have given the all. Okay, so all variable, this is double underscore all. So if your thread IDX value is less than 100, this is a predicted have been given. This is just a condition. So if we didn't give any, so this is a kernel K under kernel. So we have given the predicate and the all keyword. So if it is divided by 32 equal to 0, we are printing that particular value. That's all. Okay. We'll be getting 1, 1 and 0. Okay. So here the kernel is launched for 1, 128, one block, 128 threads. Okay. So if you could calculate, you will get that. It's for all. Here also they are telling that both the things are depreciated. Okay, so we'll move on to next one. So here it is, they have used any. Is here. That only I can put it here. Okay. Close bracket is missing. The one. See here for any. So the same program here any is given. Okay. So 1, 2, 3, 4. 4 threads have been given for any. So next one is palette. So if the thread IDX value is less than 0, 0, so it will return only one thread. Okay. So the thread value, okay, that is shown here. So here, if you have given the predicate value is something different, you'll be getting the different what is called thread value. Okay, so here for var voting, so you can use the atomic function because mainly it is used for the reduction and all. And so if some condition atomic increment, so counter the n value. So it will execute many threads in a particular var, but not all the threads. Okay, so it will execute many threads, but not all the threads. Here, you can optimize with the keyword ballot. Okay, so you can use the ballot, and here the contention is also very high. And what the leader will do is it will collect the var count, and the ballot provides the mask for that. And actually you with the help, there are different functions are available. With the help of those functions, so you can return what is set in the bits, what the first set of bits in the LSB, MSB, all those things we can get that likewise in the previous programs. Okay, so like execute after set is completed, leader performs a single atomic add. Only one atomic add operation will be done by the leader. Leader is the one who will be who is the thread which is satisfying that particular predicate. Okay, so it will be very much useful for performing atomic add only a single operation. Okay, so it also reduces the contention in that particular thing. So other functions available are POPC mask, FFS mask. Okay, so these are all the other functions. So using that functions, you can set the bits. Okay, which number, what side of bits. Okay, so want to mask. Okay, so if you use POPC, it will reduce number of set bits. FFS mask returns first set of bit. Okay, from LSB. Okay, least significant bit. So from where it will do the masking. So in what consolidation? Okay, so this one for this particular one, and if condition atomic INC counter, so you can give the ballot with some conditions. Okay, so if your thread IDX is modulo division 32 equal to 0, so you can perform the some atomic add operation with the help of this POPC mask. So POPC mask provides how many number of bits you are going to mask. Okay. It's W3. Okay. So here, what is the val? Val is given from ballot. Okay. So even though we have used so many threads, and we'll be getting these many threads. So in that POPC, okay, so it will provide the number of bits. So you are going to mask. Okay. So first thing it is telling that 32. Okay, here we have dividing thread IDX dot x divided by 32. Okay, so you will be getting a less number of only four values only. So you can say that 128 divided by 32. So you'll be getting 4. Okay, correct. Okay, that is the 4 value. It's again random. Here we are getting some other way. So here it is random only. So next is conditional warp voting, and with it will be executed with some conditions. Okay, some thread may be masked and would not participate in the masking. Okay. So here, what is ballot? Less than 100. See here, one more condition is given here. I have to give. If thread idx dot x modulo division 2 equal to 0. It will mask. Let's see. The ballot. And go copy this. Okay, we'll be getting 16, 16, 16, 2. Anyhow, 4 only. So before that, we are having one condition. After that, we are executing the ballot. So then, what all the threads are going to be masked. Okay, that we could see. So here we have given 32, no? Then when we getting 4, change this. What happened? I don't know exactly. Okay, so it is increasing. Okay, so we didn't execute that some of the programs. We try to execute. Otherwise, I will do that. Okay. Sorry. So no one is getting zero. That is the problem here. I don't know what happens this one. Value. Yeah. This and yeah. I have found the error in that. We didn't give this one. That is the problem. Okay, we got it. So if you didn't get the STD IO address, it won't the printf won't be executed. So that way that error came. Okay, so these are all some advanced topics in CUDA programming. So for atomic and reductions and all, and so some more thing is available in multi-dimensional arrays. Okay, so that thing we'll see in the next class. Okay, last class tomorrow. So also we see how to execute Python programs using GPU. Okay, so those two topics we'll see in tomorrow's class. Okay, thank you. So if you are anything else, any other doubts, you can ask me.